Hello, welcome again. We are covering the topic gas turbine cycle for civil services means IFS and gate aerospace. And in this, the first subtopic is idle cycle. So the idle gas turbine cycle is started from the compressor inlet at point A. Air is sucked in the compressor and it is compressed in the compressor. Then uh, this air is fed to combustion chamber where fuel or internally or externally may heat this air, and then this exhaust is fed to turbine which produces work and drives this compressor also. And this air at the exhaust, air or air tube lifted at the exhaust may be returned to compressor or can be exhausted to atmosphere depending upon the type of cycle, open cycle or closed cycle. So this is the typical diagram of the cycle. 1 2 process is your isentropic process ideally, and 2 3 is your heat addition process, that is your constant pressure process. 3 4 is also isentropic process. This is isentropic work done. This is isentropic compression. This is isentropic expansion. And 4 1 is it may be cooling process, or it may not be taken if we are exhausting it. Okay. So here some of the assumptions are made for this cycle. First assumption is compression and expansion processes are reversible and additive. It is isentropic. So the compression process is in compressor, that is 1 2, and expansion process is in turbine, that is 3 4. Both are isentropic and reversible or adiabatic, or you can say reversible, adiabatic or isentropic. Second assumption is change of kinetic energy of the working fluid between inlet and outlet of each component is negligible. It means the air is entering the compressor with the same velocity at which it is leaving the compressor, or we can say air is entering the combustion chamber is with the same velocity as it is leaving the combustion chamber, or we can say air is entering the turbine with the same velocity at which it is leaving the turbine. So there is no change in kinetic energy within the component. So change of kinetic energy of the working fluid between inlet and outlet of each component is negligible. Third assumption is there are no pressure losses in the inlet ducting, combustion chamber, heat exchanger, intercooler, exhaust ducting, and ducts connecting the components. So there are no pressure losses if we are assuming it as a constant pressure process. So there is no pressure loss in between. Or if we are heating the air with the exhaust, then there is also no pressure loss. So uh, there is no pressure loss in the processes in which we have assumed pressure is constant. Pressure loss is not there. Here pressure in compressor, the pressure is increasing, okay, and in and it is providing high pressure ratio, and in turbine the pressure is decreasing, that pressure decreasing due to drive the compressor or to produce work output, but loss is not there. Okay. So there are no pressure losses in the inlet ducting, combustion chamber, heat exchanger, intercooler, exhaust ducting, and ducts connecting the component. Fourth assumption is the working fluid has the same composition throughout the cycle and is perfect gas with constant specific heat. So here we are assuming that although we are compressing air and we are adding fuel here, but we are assuming that the working fluid is same within the compressor or within the combustion chamber or within the turbine, and has same property, has same value of Cp and same value of gamma throughout. Next assumption is the mass flow of the gas is constant throughout the cycle. So mass flow is constant throughout the cycle. Next assumption is heat transfer in a heat exchanger assumed counterflow is complete. So if we want to heat this air at 2 from the exhaust of the turbine, then heat transfer will be completed. So this air will be heated up to point 4 or T4. Okay. And this air will be cooled up to point 2. So exchange is complete, and we will take counter flow arrangement. Similarly, if we don't employ heat exchanger, if we use heat exchanger here also, the rise in temperature of this working fluid will be fall in temperature of the working fluid will be equal to the fall in temperature of the working fluid we are considering. So heat transfer in the heat exchanger, assume counter flow is complete, so that the temperature rise on the cold side. This is a cold side, temperature rise in the cold side is maximum possible and exactly equal to temperature drop on the hot side. So this is your hot side. So whatever temperature drop here will be the temperature increase here. This, when we consider heat exchanger. Okay, so now these are the assumptions. These are the 6 assumptions for simple cycle as well as for regenerative cycle as well as for reuse cycle. These assumptions are common for all these cycles.